Hi, and welcome to day 5 or Friday of our APCSA professional development. Today, we're going to talk about the last 2 units in APCSA, inheritance and recursion. We're going to cover some of the stickier points in the content where you should watch out for students getting stuck. Then we're going to talk about misconceptions around recursion, specifically the different buggy mental models students have for how recursion works. And finally, we only have one evidence-based pedagogy today, which is Parsons problems, one of my absolute favorites and super easy to implement inside of Codio. So to get started, let's talk about the content and sticking points. So like I said, we're in units 9 and 10 finally. A couple of sticking points are just this relationship between super and subclasses. Really specifically, which one is which? They both start with S and U, and trying to remember which is the super class versus the subclass gets extra confusing because you use the super keyword inside the subclass, and just keeping that straight is a little bit difficult. Overriding methods, which one actually gets called in different situations, gets sticky. And recursion, just as a concept, is pretty hard. So looking at superclass versus subclass confusion, we actually start with an example to try to make it a little clearer. The superhero class is actually the subclass in this case. And so you have the person class as your superclass, the superhero class is your subclass. Clearly we should name it a sidekick. And just keeping this straight and what this relationship is. So if we actually go to the next page, it talks about this hierarchy of inheritance being this downward flow where the superclass inherits things, or sorry, the subclass inherits things from the superclass. You can see even I'm struggling to talk about it and keep them straight. So the superclass passes to the subclass. The parent class passes to the child's class. And so that's really sticky and confusing, and trying to track superclass versus subclass is very, very difficult. And so just the more you can really emphasize that before moving on, the better, because it's just going to get extra muddy if they get past 9.1 and they're still trying to figure out which one is superclass and which one is subclass. Similarly, this idea of method overriding, of overriding superclass methods inside the subclass, it gets really messy because if I use a superclass object instance, it uses one method, and a subclass object instance uses a different method, but the methods have the same name. And so that gets a little confusing. So we asked them to try it out, override the say age function instead of just I'm this year's old. The superhero says something a little more cliche, and giving them the solution of actually how to say age. It's pretty simple. It just needs to happen inside of the superhero class. Finally, recursion. So we rely pretty heavily on graphics because the code doesn't help us too much. And so something like 5 factorial you see is 5 times or n times the next call. Well, the next call is 4 factorial, which is 4 times the next call, which is 3 factorial, which is 3 times the next call, which is 2 factorial. And so to see this nesting and how these different calls are returning different pieces, to make this a little bit more clear, we kind of illustrate it out for them that it's 5 times factorial 4, 4 times factorial 3. And notice we're doing the call stack here, right? We're going down, doing all of our function calls, and now we're doing back up the call stack. There are 2 parts to recursion: the going down, doing all the calls, and then the going back up, returning all of the values. So really, really important you emphasize there's kind of 2 pieces to that flow, down and up, and we're going to talk about that even more. So going back to our slides, let's really focus on those recursion misconceptions. So the very first model of students understand recursion is it doesn't work. You cannot call a function inside its own definition. This is called the null model. This just breaks. You can't have this function call inside of itself. That's just not valid. And we're going to have the same problem on the left here for all of these examples. What's going to change is the student's understanding of that on the right-hand side here in the purple text. So another way to understand this is the magic model. These are both kind of your where students start, like this doesn't work or it works by magic. So magically, this works. They recognize, oh, this calls itself, recursion, got it. But if you ask them how, magic. There's no explanation that's mechanical. And this is kind of where students start, and that's okay. And we're trying to push them to more complex and nuanced understandings of recursion. Sometimes they see math and they're like, cool, I got it. I can do math. And so what they'll do is they'll start to fixate on the math itself. Okay, 4 times this thing plus 3. Okay, so I can pull out this this 1/2, or I can plug in, oh, well, n is equal to 8. Okay, so I'm going to do 4 times, okay, 8 over 2 is 4. So 4 times 4, and I get my 16, and okay, plus 3, and they get 19. And they just completely ignore the recursive piece. That C just kind of gets dropped out if they're so busy solving the math. And they're just clinging to the familiar because this is hard. This is another more naive way of trying to solve recursion. So if you start seeing answers that have kind of funny numbers, look at, can you take this as a math problem? So similarly, trying to calculate a value before the next recursive call is enacted. And so trying to combine those, this can look pretty similar to the algebraic model. So I'm going to do 4 times something plus 3, and I'm kind of trying to connect, okay, well, 4 times 1 plus 3 is 7, and then I'm going to add 7. So 4 times 2 plus 3 is 8. That's 11. So I'm going to take my 11 and my 7 and combine them. And that's not exactly how that works because I should be passing my 7 back instead of just using 2. So you can see how they kind of understand you're combining different versions of this, but exactly how they're handling the return isn't quite right. So active models. So we're starting to get a lot closer to a more complete and canonical understanding of recursion. So they understand that first part of the recursive call. I'm going to call, in this case, 8, then 4, then 2, then 1. I got it. That's how we recurse. We go down into the base case, and then 1 is 1. Good. But they don't understand that second part, the coming back up, that the 1 gets plugged in here, and then that value that's returned gets plugged into the n is equal to 4 place. The down is fine. That kind of trickling the value back up is completely broken for them. They lose that second half of the recursion. So there's also the opposite of this. They understand that the value works its way up. And so they kind of just start with the base case and keep going up and hope they hit whatever that n equals 8. And so their struggle specifically with these smaller numbers. So like if you tried to do something like n is equal to 1, well, they get in here and they're like, well, I can't pass that back to anything. they only understand that like trickle up. And so if you don't have much trickle up, it gets a little messy for them. The step model. So this is, you do it once, maybe twice, and then you're done. They kind of have a limit of how many steps you can go through. So maybe you run through this recursive function once, and that's the return value. Maybe use the base case. So I'm going to take this one, plug it in here. Okay, so this is 1. And 4 times 1 is 4, plus 3 is 7, the answer is 7. They do like one step of the process without getting all the way to the answer. The hardest kind of fuzzy model to catch, or the flawed mental model to catch, is looping, because it works in some cases. So I can use this as a loop until the base case condition is met. So I can kind of work my way opposite actually for this one. So 4 times 1 is 7 plus 3. And then I'm going to go and do my 2. So I do my 7 times 4 is 28 plus 3 is 31. And I do my 31 times 4, and I would need a calculator, plus 3, and go back in. Where this breaks is when you do things like the Fibonacci sequence and you have multi-tailed recursion. For single-tailed recursion, no problem. It's basically a loop there. This will work. The second you start doing multi-tailed recursion, though, it breaks down on them. So the last piece today, I know we're going pretty quick, is evidence-based pedagogy, and today's topic is Parsons problems. This is a really great formative assessment, and one of the most powerful pieces is it's a lot less time to solve a Parsons problem for your student compared to writing code or fixing buggy code, but there's no statistically significant difference in student performance, knowledge retention, learning gains. We've also seen that as students kind of go on in a course, particularly an interactive ebook context, their engagement wanes. They stop clicking on things, trying things out. But Parsons problems, the amount of interaction those get remains pretty high, particularly compared to actually solving coding exercises, because there's such low-hanging fruit. They're so easy to try and solve. And so one of the things you can pretty easily do is take one of your existing solutions to a coding exercise. You can just drop it into this code to become blocks. If you want to add distractor blocks, which are blocks that are incorrect. And then it'll spit out a Parsons problem for you. So for example, from our overriding methods section, so we're going to assume I have this athlete class, and that's my super class, this ball player class, which is my subclass because it extends athlete. Here we go. We have super inside my subclass. And we're passing, okay, name and sport. Got it. And then I'm going to override the describe method inside baseball, so it returns the player's batting average. So in this case, I had this double, that's his batting average. So I need to override public string decide or describe. Okay, so this is my method header. I need to have exactly the same method name, so I can't use my capital D. It's returning a string, so this void does not work. I guess the question is, do I need to pass in the batting average? And the answer is no, because I'm inside my my class. Then I'm going to return, and look at that. I can indent, practice good form factor, and then check it and get a cool explanation. And so this was much faster than if I had to write this completely from scratch, but I'm still doing the same thinking and specifically presenting convincing incorrect answers, just like back when we talked about peer instruction, is a really good way to target misconceptions. If you're If there's something that is a little bit sticky or confusing, you can try to tempt them with something that looks good but isn't correct. So that kind of wraps up our professional development for the week. Thank you for joining us. And we're here to continue to support you as you implement Codio, whether it's with one of our partner pieces of content like We Teach, You Teach, our introduction to Java stuff, our APCSA content, or really anything. You can start by using our docs, which is labeled as Help Center in that left-hand side of the Codio interface. Down here, there's also support chat. So if you can't find an answer in our documentation, you can talk to our support team Monday through Friday, 5 to 9 Eastern, 5 a.m. to 9 p.m. Eastern. Gives you pretty good coverage through Europe to the West Coast of the US. And if you really want someone to walk you through a particular feature, say you want to implement Parsons problems for the very first time and you want someone to walk you through how to do that well, you can actually schedule a success meeting using this link. If you have any questions at all, feel free to reach out to us. We'd love to hear from you.